Hey guys, welcome back to my channel. Today, this is the last video of the GCSE chemistry series, topic 10, using resources. Before we jump in, feel free to subscribe if you want to see my other GCSE chemistry videos or any other subjects that I do. You can find all of the GCSE chemistry videos as well in a playlist on my channel. And of course, like the video as well if you found it useful, and comment below any questions you have. Either myself or your fellow students will get to it and answer it for you. But let's just jump straight in. First, we have using Earth's resources and obtaining potable water. So we use the Earth's resources to provide warmth, shelter, food and transport, and this includes natural resources supplemented by agriculture, provide food, timber, clothing and fuels, as well as finite resources from the Earth, such as oceans and atmosphere, which are processed to provide energy and materials. Chemistry plays an important role in improving agricultural and industrial processes to provide new products and in sustainable development, which is development that meets the needs of current generations without compromising the ability of future generations to meet their own needs. Renewable energy resources are sources of power that quickly replenish themselves and can be used again. Only include plants or wood if they continue to be replanted. Potable water is water that is safe to drink, but it's not pure as it contains dissolved substances. And to produce this in the UK, an appropriate source of fresh water is selected, usually lakes, rivers, or the ground. You usually see on certain bottles of water, whether it's come from a mountain or something, which is then passed through filter beds to remove different insoluble solids, and the water is sterilised to kill microbes. Sterilising agents include ozone, UV light, or chlorine. Much like in a swimming pool you'd have chlorine, that's to help sterilise the water. If only salty water is available, desalination is required, which can be done via distillation or using membranes. So an example of this is reverse osmosis, but both are very expensive, so obviously it's preferred if there's a fresh water source. Water of the correct quality is essential for life and must be free of poisonous salts and harmful microbes. Correct quality water is produced by passing water through a mesh screen to remove large bits. Chemicals are then added to make solids and microbes stick together to form sediment and sink. Then an anaerobic digestion of sewage slide before being sterilised with chlorine. This is relatively cheaper and easier to obtain potable water from groundwater and wastewater, obviously in comparison to salt water, although seawater is good for countries with little fresh water. I feel like I've said water way too much and now it sounds weird. Alternative methods of extracting metal as well. So Earth's resources of metal ores are limited. Copper ores are becoming scarce, and new ways for extracting copper from low-grade ores, including phytomining and bioleaching, which avoid traditional mining methods and moving large amounts of rocks. Phytomining uses plants to absorb metal compounds, where plants are harvested and then burned to produce ash that contains metal compounds. And bioleaching uses bacteria to remove leachate solutions that contain metal compounds, which can then be processed to obtain the metal. Luckily, the exam is not a speaking one, otherwise I would have failed. Life cycle assessment and recycling. So firstly, looking at the life cycle assessment, this is carried out to assess the environmental impact of products in each of these stages. So extracting and processing raw materials, manufacturing and packaging, use and operation during its lifetime, disposal at the end of its useful life, including transport and distribution at each stage. Use of water, resources, energy sources, and production of some waste can be fairly easily quantified, and allocating numerical values to pollutant effects is less straightforward and requires value judgment, so life cycle assessment is not a purely objective process. Selective or abbreviated life cycle assessments can be devised to evaluate a product, but these can be misused, for example, in support of claims for advertising purposes. Then we've got reductions in use. Reusing and recycling of materials by end users reduces the use of limited resources, use of energy sources, waste and environmental impacts. Metals, glass, building materials, clay, ceramics and most plastics are produced from limited raw materials, And much of the energy for the processes comes from limited resources, and obtaining these raw materials from the earth via quarrying and mining, which can cause environmental impacts. Some products, such as glass bottles, can be reused as they can be crushed and melted to make different glass products, whereas metals can be recycled by melting and recasting or reforming into different products. So amount of separation required for recycling depends on the material and the properties required for the final product. For example, scrap steel can be added to iron from a blast furnace to reduce the amount of iron that needs to be extracted from an ore. And then we have corrosion. So corrosion is the destruction of materials by chemical reactions with substances in the environment. So an example of this is that iron rusts from the reaction of air and water. But corrosion in general can be prevented by applying a coat that acts as a barrier. And examples of this is greasing, painting, electroplating, and specifically aluminium has an oxide coating, and some coats are more reactive, so this works as a form of a sacrificial protection. An example of this is zinc is used to galvanize iron. The more reactive metal donates electrons to any ion of the other metal that may have formed to avoid corrosion. Most metals in everyday uses are alloys, so pure copper, gold, iron and aluminium are all too soft for everyday uses, and so are mixed with small amounts of similar metals to make them stronger. For example, gold is usually an alloy with silver, copper, and with silver and copper, and the purity of it is measured in carats. Bronze is an alloy of copper and tin for electrical connectors, and brass is an alloy of copper and zinc for tools. Steels are alloys since they used fixtures of carbon and iron. Low carbon steels are easily shaped, so sheeting, for example. High carbon steels are hard, so cutting tools. And then stainless steels containing chromium and nickel are resistant to corrosion, hence why you'll usually see cutlery with stainless steel on it. And then aluminium alloys are low density, so this is often used with aircrafts. Then we have ceramics, polymers and composites. So soda lime glass is made by heating a mixture of sand, sodium carbonate and limestone. Borosilicate glass, made from sand and boron trioxide, melts at higher temperatures than soda lime glass. Clay ceramics, including pottery and bricks, are made by shaping wet clay and then heating in a furnace. Properties of polymers depend on what monomers they are made from and the conditions under which they are made. Low-density polythene and high-density polythene are both made under different reaction conditions using different catalysts. So low-density polythene has weak forces of attraction as the chains are further apart, meaning it has a low melting point and is soft, whereas high-density polythene has stronger forces of attraction as the chains are closer together, giving it a higher melting point and it makes it much more solid. Thermosetting polymers are made of individual tangled polymer chains which are easily separated and are melted by heat. There are weak intermolecular forces between the chains, so are easy to separate at lower temperatures, and less heat energy is needed to break the chain. Thermosetting polymers consist of polymer chains which cross-link so they do not melt when heating. Most composites are made of two materials, a metric or binder surrounding and binding together fibres or fragments of the other material, which is called the reinforcement. So examples of this is bricks and pottery. Then finally we have the Haber process and use of NPK fertilisers. So firstly looking at the Haber process, so this is used to manufacture ammonia, which is used to produce nitrogen-based fertilisers. The raw materials within this are nitrogen, hydrogen, and the nitrogen is obtained from the air, and hydrogen may be obtained from natural gas or other sources. The purified gases are passed over a catalyst of iron at a high temperature, about 450 degrees Celsius, and a high pressure, about 200 atmospheres. Some of the hydrogen and nitrogen reacts to form ammonia, but this is a reversible reaction, so the ammonia can break down again. On cooling, the ammonia liquefies and is removed, and the remaining nitrogen-hydrogen is recycled. The Haber process is in dynamic equilibrium, so the forward and backward reactions keep going once equilibrium is reached. You can see here the chemical equation. That's not, just to clarify, there's not meant to be two twos on the end of the hydrogen. That's just 1, 2, Apologies for that. So there are less. So as you can see here in the chemical equation, there are more moles on the left-hand side on the reactants than there is on the product side, which means to increase pressure, so if you increased pressure, equilibrium moved to the right, so more ammonia is produced. Hence why you have a very high pressure with this process. The forward reaction is exothermic as well, so a low temperature would favour towards the reactants, more ammonia was produced. However, the actual conditions used are not low temperature and very high pressure, because a low temperature leads to a reaction rate that is too slow, and a very high pressure requires too much energy. So even though the conditions it's in are not perfect, they are kind of the best of both worlds to make this reaction and this process as effective and productive as possible. Then we have NPK fertilizers. So NPK stands for nitrogen, phosphorus, and potassium, obviously based on their periodic table symbols. So compounds of nitrogen, phosphorus, and potassium are used as fertilizers to improve agricultural productivity, and NPK fertilizers can contain compounds of all three elements. Industrial production of NPK fertilizers can be achieved using a variety of raw materials in several integrated processes. NPK fertilizers are formulations of various salts containing appropriate percentages of the elements. Ammonia can be used to manufacture ammonium salts and nitric acid. Potassium chloride, potassium sulfate, and phosphate rock are obtained by mining, but phosphate rock cannot be used directly as a fertilizer because it's treated with nitric or sulfuric acid to produce soluble salts that can be used as NPK fertilizers. So that is everything for today. I hope you found this useful. Please, of course, again, let me know if you have any questions in the comments and I'll try and get back to you, or potentially your fellow students may get back to you before I can. But I hope you enjoyed, and yeah, I would really appreciate it if you subscribed and liked this video.